There are some problems that are upstream and high leverage such that solving them renders a bunch of downstream problems tractable or even trivial. And I found that very motivating, and I realized that if we can solve intelligence, if we can make the methods undergirding AlphaGo scale to real-world problems that are noisier, higher dimensional, and make them economically viable at that scale, then we could potentially solve a lot of downstream problems very, very quickly. One of the cool things about technology is it's not zero sum. We're trying to find new and better ways of doing things, and we can grow the pie. We don't have to kind of divvy up the pie. And I think that in areas that are growing quickly in technology, there's a lot of co-opetition, and a lot of classical dynamics and ideas around competition don't apply.
Hello and welcome to 1 to 100, a podcast that takes you inside the most promising hypergrowth startups in a conversation with the founders themselves at the helm. Our goal is to give you the inside story alongside empirical analysis of a notable tech company that you might want to join. I'm your host, Usman, the author of the Why You Should Join newsletter. Welcome to 1 to 100, where every week we sit down with the founders of some of the most notable hypergrowth startups. As always, my name is Usman. I'm one of the co-authors of Why You Should Join and the host of the podcast. Today's company, Foundry, also known as ML Foundry, is on a mission to orchestrate the world's compute capacity. They have a lot of companies using their platform, ranging from enterprise clients all the way to frontier startups. Not to mention, their platform is growing rapidly with their usage doubling month over month. They recently closed an $80 million seed and Series A round, co-led by Sequoia Capital and Lightspeed Ventures, with participation from Redpoint, Microsoft Ventures, Conviction, just to name a few. I'm super excited to be chatting with Jared Quincy Davis, the company's co-founder and CEO. Jared, thank you so much for doing this.
Thank you, Usman. You're really good to see you, and looking forward to the conversation.
Awesome. Well, let's just dive right into it. So the high-level mission here is to orchestrate the world's compute capacity. I guess the follow-up to that is, how exactly do you do that? What is the product offering today?
Yeah, great question. Our mission is somewhat framed technically for people joining our team, funnily enough. From a customer perspective, the way that they think about it is Foundry is an AI cloud. We're a new breed of public cloud built specifically for AI workloads, and our goal is to address some of the hardest things about being an AI practitioner, so that the types of things that right now only OpenAI and DeepMind can do, a much broader class of people can do. So we've tried to address some of the economic impediments to doing frontier things in AI, and also some of the ease of use challenges that arise pretty frequently. And we provide this through a public cloud infrastructure as a service platform that people can use. And we made a bunch of optimizations under the hood that make things that are really hard around GPU reliability, instance configuration, and kind of jobs management a lot easier on the ease of use side. That a lot of those economic points, a lot of those ease of use points, including the points around reliability, have economic implications, and that's the other main bucket, economics. And we've tried to give people a lot more elasticity, so they're only paying for GPUs when they're using them, but also do a lot of things from a scheduling perspective to drive the cost per GPU hour down substantially. And so we've been able to cut the cost for many workloads by 12 to 20x baseline at scale. And that's leading to a lot of really exciting usage from a lot of awesome companies doing cool things that they believe they wouldn't be able to do otherwise outside of Foundry. And that's really, really exciting. It feels like we're making a counterfactual contribution. And so that's what motivates us to keep working on this and to put a lot of our soul into it.
Yeah, that's awesome. Well, we're definitely going to dive into a lot of the fun stuff that you guys have built to make this experience so much better for those who are wanting GPUs. Before we get into the nitty-gritty details, I'm curious what made you passionate about this mission in the first place. And I think this will probably open up the question of like the founding story, like what got you thinking about this problem. I'd love to hear all of that from you.
Yeah, in terms of why I worked on this and why I work on this and decided to work on this, early in my education, I was quite excited about a lot of topics. There are many things that are interesting and a lot of hard problems and a lot of exciting problems. I thought fusion was very interesting. I was very interested in some material science challenges around things like room temperature semiconductors. Quantum computing seemed like it'd be fascinating one day, potentially. But the thing that AI definitely stood out, and the thing that made AI stand out the most, was I saw AlphaGo from DeepMind in 2015. It was pretty clear to me that that method was actually, although it was just playing the game of Go, it was representative of something much broader, much more general and extensible, and that it was kind of showing the shape of a solution that could be applied to a pretty broad range of combinatorial optimization problems downstream. And that a lot of really important downstream problems have that same mathematical character, that same shape as the problem that AlphaGo is tackling. And so that made me realize that there's this kind of a concept of a problem hierarchy. And one way that I think Demis always puts this, I thought found really inspiring, was he talks about root node problems and how there are some problems that are upstream and high leverage, such that solving them renders a bunch of downstream problems tractable or even trivial. And I found that very motivating. And I realized that if we can solve intelligence, if we can make the methods undergirding AlphaGo scale to real world problems that are noisier, higher dimensional, then and make them economically viable at that scale, then we could potentially solve a lot of downstream problems very, very quickly, problems that would otherwise be completely intractable. Things like fusion. Maybe deep learning is the best way to solve fusion. Some of the problems around health and aging, right? And we've seen that in how AlphaFold is now a key part of a system. It's now a key part of our ongoing attempts to address, to basically improve our understanding of mechanisms of disease and to design drugs to tackle diseases. It's pretty inspiring. I think the really remarkable thing about deep learning that also, if you follow that line, leads us to Foundry is, turns out the thing that I think inspired a lot of deep learning's pioneers is they did realize that deep learning was a root node problem, that if we could solve deep learning, we could solve a lot of downstream problems, and that turned out to be true, I think, on a faster time scale than any of us could have envisaged. The state-of-the-art systems in a pretty broad range of settings, from proteomics to stock market prediction, from code generation to image generation, from recommender systems to return on ad spend prediction. The state-of-the-art systems in all these settings are deep learning-based systems. I think one of the questions that's interesting is, why is deep learning the ascended ML theoretic paradigm? And I think that I and a lot of other people believe that it's partially because deep learning, out of all the ML theoretic approaches that we've conceived of, scales really well. And so some early pioneers realized that as Moore's law continued, deep learning would get better. And what that means is that a lot of the root node problems of deep learning are actually systems problems. They're questions of how can you bring computational scale to bear. And so maybe these ML systems, ML cloud economic problems are actually kind of the root node problems of deep learning, and thus the root node problem of root node problems. That's partly how we think about it. We think it's very, very high leverage, and by addressing these challenges, we can potentially make it such that things like events like AlphaFold and ChatGPT can be a lot more common in the world. Things that only someone at DeepMind or OpenAI can do today, because only they have both the scale of compute, the economic leverage to have that scale of compute, but then also the tools that, for example, DeepMind's been building for 14 years to make it, to abstract away a lot of the complexity between the ideas in a researcher's head and a cluster. There's a lot there. And so from both that ease of use and economic perspective, I think there's a large gap. But if we can address that gap, then maybe things like AlphaFold will be a lot more common across every area of scientific and technological endeavor. And that'd be quite an inspiring thing, and feels like a massive contribution to make. And so that's a big part of what we find motivating is, can we eclipse and democratize the types of capabilities that currently are exclusively the domain of OpenAI and DeepMind?
Yeah. And I know you spent some time at DeepMind too. And so it's actually really remarkable how being there, you almost realize that, hey, I have a privilege that other people don't have. And if I could maybe give that privilege to other people building an AI, who knows what else we could see, right?
That's right. Yeah, I think AlphaFold is a really illustrative example. I believe it was initially like 3 people, later 18 to 20 people or so, and they solved a 50-year grand challenge in biology that every university, every pharma company hadn't solved. Same with OpenAI. OpenAI was 400 people or so, and they launched ChatGPT and shook up the entire global business landscape.
Yeah.
Those stories are pretty remarkable, but they're not quite the David and Goliath stories that they appear to be, right? When you double click and realize that, okay, yes, there was 400 people at OpenAI, but they also had $13 billion. And so I think there's something we said of, okay, what can we do to take the capabilities that OpenAI, the things OpenAI can do, and give those to more people? And at DeepMind, I saw this. Like, our team at DeepMind is remarkable, a very, very special set of people. Well, there are also smart people that I encountered doing my PhD at Stanford who couldn't do research at scale and had amazing ideas that definitely deserved to be tried, would be very useful, that they could not try at scale, and you couldn't necessarily know if they'd work unless you ran them at scale. And so I think that it's a disservice to humanity if those types of ideas die on the vine, so to speak.
Yeah. That makes complete sense. I guess sort of moving into your guys' approach, I'm curious, like, why does AI cloud and the AI cloud that you're building require the approach you're taking versus just these guys using traditional cloud?
Yeah, it's a really, really great point. There's a lot of depth there that we could peel, but I'll insert from here, which is that the existing public cloud implicitly and explicitly was built for the web. AWS was started in 2003, and I think in many ways, the assumptions around both how the business models work, but also all the technical infrastructure, are aligned to web workloads. AI workloads are very distinct in a number of ways. They have a different economic structure, a different shape. And that can motivate a pretty fundamental re-envisaging of how the cloud works, both in terms of the business models and the mechanisms, but also from more of a technical scheduling perspective. Things look very, very different potentially. And that can enable something new. And so part of what we've done, I think, at Foundry that's really interesting was we've asked from first principles, tabula rasa, what type of infrastructure would you need for AI workloads? What's different, right? And what infrastructure is best suited to these types of workloads, and built that from scratch. It turns out there's a lot of things you can do there that allow you to dramatically cut the cost and also address some of these burning ease of use types of challenges in a pretty new way. And so I can touch on a couple of the things that are pretty unique about AI workloads.
Yeah.
And unfurl that. So I think there's maybe four I'll highlight that are things that are quite different about AI workloads as compared to classical cloud workloads. One is that AI workloads are subject to contiguity constraints. And so a lot of these AI workloads are quote unquote large workloads. And one definition for large is that they require multiple servers all working on the same workload synchronously. That's kind of the large regime, one definition for large regime. And so these servers need to be interconnected for this to be kind of a viable thing. If they're not interconnected, then it's much more difficult for them to coordinate or to work in synchrony. And so that means that you care about shape when mapping AI workloads. And you don't care about shape in the same way for a lot of classical cloud workloads, even multi-node workloads. Kind of the servers it could be independently mapped. The communication requirements weren't as stringent. Communication complexity wasn't as strong. And so that's a very different scheduling problem, right? You don't have to do some type of AlphaGo-esque scheduling to think about clusters and opportunity costs.
Yeah.
To maybe as a very dumb example, if you have a cluster, this isn't quite technically correct for a number of reasons, but it's maybe somewhat clear to reason about. If you have a cluster of, let's say, a square that's 1,000 GPUs, and I allocate the middle 100, I have 900 empty GPUs, but I can no longer allocate a square of size 250. That's actually very challenging for my economics if I'm the owner of that compute. If a lot of the workloads are of some minimum size. You can have a lot of empty GPUs, so there can be both a glut of servers, but a shortage of servers in the right configuration. That's a very challenging thing from a scheduling perspective that doesn't quite apply for CPU workloads classically in the same way. So that's one. A second element that's a bit different is GPU workloads and AI workloads are much more subject to dynamics around affinity. Meaning in CPU land, this is not quite as true, where depending on the type of CPU you run the workload on, you'll see a massive order of magnitude dispersion in price performance. But that is true for AI workloads, where depending on the nature of the workload, and it differs by workload, it differs for different types of training workloads, for different inference workloads, you can see a massive dispersion in price performance if you run that on, for example, a state-of-the-art server as compared to a slightly older generation of server. That's especially true for certain workloads that require the state-of-the-art server, but many workloads wouldn't actually experience any acceleration if you ran them on the state-of-the-art server. It depends on where the bottlenecks are and what the constraints are, and that's different. And the magnitudes are also different for AI workloads, and that means that you have to consider this when scheduling in a bit of a new way. It makes the scheduling problem more important and increases the gains from doing this well to a substantial degree. The stakes are also higher for two more reasons, and then I'll pause. The first additional reason is the economics are very different for AI workloads. The TCO, the total cost of ownership, is dictated by CapEx rather than OpEx to a very unique degree. Most other assets, OpEx and CapEx, contribute relatively evenly to the total cost of ownership. So if you buy a plane, the cost of a plane is a pretty even mix of pilots, fuel, and the depreciation of the plane over 20 years. That's not true for AI servers. These AI servers are quite expensive, but the actual incremental cost of power is quite low. The TDP of an H1 server, for example, can be 10.6 kilowatts. At the average cost of electricity in the US, that's roughly $1.06 per hour, 10 cents per kilowatt hour. Obviously double it because of cooling, but you can have it because data centers often have cheap power. You're talking roughly, let's say, on the order, to make it simple, of $1 per hour to run that server incrementally in terms of power cost. And maybe there's some additional OpEx from damage, etc. But relatively de minimis compared to the fully loaded cost, including CapEx, which, depending on your assumptions on depreciation and lifetime for that server, might require you to charge $98.32, which is the AWS on-demand price, for instance, or $40 for that box, something like that. So it could be a couple, like an order of magnitude to a couple orders of magnitude difference in cost between fully rationalized prices per hour and the incremental cost of power. That's very unique, and that means that incremental utilization is essentially free, and you really want to maximize utilization. And so you need to have potentially even a very different business model around that. And so, for example, that fact partly required Foundry to do something a bit unique, where we got rid of the kind of indeterminate on demand, where you don't know when an instance allocation will start or end. We actually do not provide that. We only provide short-term reserved and long-term reserved allocations where we know the start and end, but then also spot and preemptible allocation. That way we can bin pack, and that allows us to generate a ton of efficiencies that we can pass on to customers in the form of lower costs. But without a lot of work that we've done to make using these form factors very convenient for people, might be difficult to adapt their workloads to this setting that we have. So that's another difference, and I'll pause there. Those are three. I can note one more, but there are a number of things that are very different about AI workloads, and they motivate and I'd argue necessitate a pretty different approach for business model, but also technical perspective to building a cloud. And I haven't seen other people build clouds in a fundamentally new way, taking advantage of these unique attributes to drive kind of new classes, new degrees of gains.
Yeah. No, I mean, I think that was a masterclass on sort of why, the new AI world requires a new cloud as well. And we'll definitely dive into a lot of these optimizations that you guys have made to utilize GPUs better and make the experience so much better for those who are using Foundry. But kind of going back to the people who are using Foundry for a second, what do these people look like? I mean, what is your demand really? Are these hobbyists? Are these large companies? Are people using it for inference or training? I just want to set the stage by first even figuring out, like, who do you see coming to your site a lot and using your product?
Yeah, for sure. So this is a very awesome question and very exciting. Our customers are all quite cool. The one distinction that might be helpful to draw to talk about our customers is I'll draw maybe two distinctions. One between what I'll call AI developers and developers who want to use AI. This sounds quite similar, but actually this is a pretty meaningful substantive difference in terms of what they care about and what's challenging for them and the types of tools that they need to be effective. That's one distinction. The second distinction I'll draw is I'll ask a question of at what stage in the development lifecycle are you helping them? Are you helping them in the kind of early phases where they're trying to do preliminary experiments, typically at very small scale, to validate whether AI works for a given application, to validate the business case, etc.? Are you helping them at the stage where they've got those early embers and they're trying to scale that into a full-fledged configuration and put something in production, do large-scale experimentation, large-scale development and pre-training, and then take that to prod? Very different challenges at these different stages, different things that you care about. Ultimately, I think all of infrastructure, the entire infrastructure value proposition is typically about economics in some way, obviously. That's overly reductionist, but somewhat useful. Ease of use versus economics, the distinction I drew earlier. Ease of use matters more than economics, for example, price performance, when developer time is a lot more valuable than, for example, the infrastructure cost and efficiency differences. In that case, things that save you developer time are much more important than the cost of the service, etc. That's especially true when you're doing small scale development, for example, or small scale experimentation. You don't need cost optimization yet, for example. On the other hand, for people who are trying to put things in production or do things at large scale, or for whom AI is a core part of their economics, which a lot of AI first companies, whether the largest public companies like Google or small startups, they're spending more on AI compute than they're spending on people. And so when you get to that stage, you actually care a lot about economic concerns that may not matter at small scale.
Yeah.
You also, when you're starting to put things in production or scale things up, care about things like reliability and security that aren't issues at small scale in experimental settings. And so this changes the types of technical problems that an org targeting helping different types of people would address and prioritize versus those that they would not. So we focus mostly on AI developers for now, not developers who want to use AI. We've also focused mostly on the types of issues that are most acute when people are trying to do large-scale experimentation and really push the frontier, technically, or put things in production. And those are largely concerns around reliability, for example, and economics. And so that I think has dictated a lot of our technical roadmap and the types of things we prioritize. And this is true for we've prioritized. I think this we made these distinctions and prioritized this class of user for a lot of reasons, both morally, but I think there are also a lot of strategic and sequencing reasons that we can get into for why we focus on this class of users. Let me pause there. That was a lot.
Hey, 1 to 100 will be right back after a quick word from our sponsors.
Our sponsor for today's episode is Carta, the end-to-end accounting platform that's purpose-built to power the strategic impact of the fund CFO. For the first time ever, private fund operators can now leverage their very own bespoke software that's designed from the ground up to bring their whole portfolio together, enabling formations, transactions, and distributions to flow seamlessly and accurately. The end result? A remarkably fast and precise platform that empowers better strategic decision-making and delivers transformational insights on demand, timely K1s, holistic fund performance data, and so much more. Come see the new standard in private fund management at carta.com/investors. That's carta.com/investors.
Yeah, I'm actually curious. Yeah, why focus on that class of consumers? Because this is, as you know, like a obviously a huge market. We're going to dive into how there's a lot of different players with different angles. So I am actually very curious, like why this segment?
Sure. Yeah. So I think there's a couple of reasons. There's a sequencing reason, which is primarily how we thought about it, but there's also a notion of there's kind of a strategic benefit as well. So number one, I think that maybe it's partially there's a notion of bias in that maybe these are the types of users that we understand most deeply and have the most empathy for, given our backgrounds in as AI developers trying to do large scale work. There's a lot of empathy for that setting and the types of challenges in that setting. That's probably a big part of it. Also, I think it turns out that type of user, I'll note, exists across organizational scales. So that type of user, AI developers trying to do things at scale, exists in enterprise settings, but also exists in startups. We're defining it more by who they are and what they're struggling with, less by some other potentially artificial segmentation. Another point I'd make is I think that there is a pretty big gap for that type of user, and that there's a lot of, I think, very exciting demos in AI, but there's actually a pretty big drop off for those demos making it into production in a timely fashion. And I think that is a potential impediment to the continued flourishing of the field. That wouldn't be great. And so I think there's a gap there. I don't think it's getting sufficient focus, and there's enough force on addressing the infrastructure gaps for that type of user trying to make that transition or trying to do that class of work. But from a sequencing perspective, I'll spend a bit of time explaining that. I think one of the things that really great companies do remarkably well is they find creative ways, and this is something I have an increased appreciation for how difficult this is. They find creative ways to distill and sequence steps towards a very ambitious, absurdly ambitious goal. Right? SpaceX is one example. SpaceX set out to make life multiplanetary and put people on Mars, for example. 22 years later, they're still not on Mars, yet they've made a lot of progress towards that. And as one of the intervening steps towards making life multiplanetary, they've created FedEx to low Earth orbit. And they're also creating, a pretty interesting telecom business using that FedEx to low Earth orbit. Pretty remarkable story, and they're making progress clearly towards Mars in a pretty inspiring way. Another great example would be DeepMind. DeepMind set out in 2010 to solve intelligence and basically pursue AGI. This was a very controversial thing to say at that time.
Yeah.
It was not received well by people in the field, so to speak. It's now a little bit less controversial to say you're working on AGI. It was quite controversial at the time. DeepMind, though, was very systematic, and I think one of the key strategic decisions Demis made was saying, yes, we want to solve AGI, but we're going to strategically decide to focus on games so that we can make clearly discernible progress towards that goal. He wanted to turn something binary into something continuous. He wanted to have a greater signal as to whether we were making progress or whether the early DeepMinders were making progress. And that, I think, was one of the great decisions they made. And I think that a lot of DeepMind founding team had a pretty clear roadmap in mind that they expressed to the team for how that early work on games will translate into work in certain kind settings. Kind meaning they have key attributes that make them viable for example, deep reinforcement learning, which we can talk about. and then how that would then unfurl and lead to DeepMind actually having a big impact on key business domains and also on scientific discovery. And I think we've seen some of the early fruits of that with the recent award that Demis and team received, John Jumper, for AlphaGo, the Nobel Prize, which is pretty remarkable. And so that's something that great companies do well. As one last example, I think Tesla's done this very well with notion of electrifying transport, and they started with a very high-end car at the high end of the market for kind of low volume for a small set of people, right? And then they've been coming down more and more. They're still not at that 25K car for the ordinary consumer, you know, many years later. But they've made a lot of progress. They're a big company, and they have done a lot to electrify transport. And so I think that's one of the really key things. And so for something that's technically very challenging in systems, the closest example for a really great sequencing was the internet and some of the technical decisions made in the development of the internet. The early internet pioneers made a key decision to focus on a layered model for building out the internet. And so the OSI model was discussed in the TCP/IP model. And ultimately, we landed on a model of building out the internet whereby different layers of the infrastructure only had to worry about their kind of slice. And the things above and below them were abstracted. So that was a key decision. And so I think we pursued a somewhat similar idea. Okay, if we want to build really great AI infrastructure experience to make really ambitious research easy to conduct, there are very high level platform as a service things you might need. But I think we decided actually it'd be a lot easier. Some of those things that are very hard to do if the infrastructure doesn't work are actually trivial. So for example, some platform as a service things like fine tuning as a service is actually very hard to do if the infrastructure is fickle, if it's expensive, and if it fails a lot, for example, and hard to configure. If the infrastructure is very easy, then fine tuning is just a script, a very light script of 50 lines of code. If the infrastructure is kind of shaking beneath you, then building some of these flows on top of the infrastructure requires a ton of additional work around redundancy. It's a much more complicated endeavor. And so part of our belief is, okay, if we first just get the infrastructure right, that'll make it easier for people to build things, ourselves or others, to build things at that platform as a service and models as a service layer, or to conduct research on the infrastructure. And so we started at the infrastructure level. But the thing about the infrastructure level is when you're solving hard infrastructure service problems, you're mostly making it easy for someone who's doing really hard things. You're making those really hard things only medium hard / medium. That's different from making medium things really easy.
Yeah.
And so we focus more on making things that are super hard only medium. And over time, maybe we can help make those medium things easy. But for now, we focus more on that side of things, empowering that type of person, trying to do that type of thing. And so that's a little bit of why we thought about targeting people that we target, and so and addressing their challenges. And so the benefit of that is all of our customers are pretty meaningful. Like they're doing a lot of serious work, and they have large scale workloads, which increases our, for example, ASPs, our average selling prices, and kind of the economics of each customer. And that's awesome, and helps with Foundry's viability. But also, I feel very privileged. Kind of a tertiary benefit that I didn't anticipate is we see things when they're starting to break out. That's when people start to care about reliability and economics, is when they're starting to scale it. And so we, I think, get a front row seat to the things that are working in AI. And so my job is awesome. Like I get to just meet customers who are doing really cool things. And they're working, and we're trying to help them make them work at scale. Or they have really awesome ideas, and they're going to make a big bet on those ideas, and they have some novel insight, or research insight, and they want to try that at some scale. We get to kind of help them manifest that. That's pretty cool. And so I think it's a particularly inspiring seat to be in.
Yeah. I'm glad you brought up this way of sort of viewing even the AI cloud as sort of like layers. Because the next question I was going to have naturally is one I have to ask was around like competition. Obviously, there's like traditional cloud providers that also provide GPUs, but then there's also a number of other pretty high flying startups that came out in the ball game. We write about this too in one of our pieces about, there's models as a service, there's functions as a service, there's all these different players. But I want to get your breakdown on all of that and how you guys fit in that layer. It almost sounds like some companies that people might consider as like competitors to you, you guys might actually be helping them provide their service. I want to get that from you.
Yeah, definitely true. Yeah, this is actually a really important point. I like the way you framed that, Usman. I think that a lot of the theory and thinking around competition was actually developed in markets that are stagnant or shrinking. It is implicitly very zero sum. One of the cool things about technology is it's not zero sum. We're trying to find new and better ways of doing things, and we can grow the pie. We don't have to kind of divvy up the pie. And I think that in areas that are growing quickly in technology, there's a lot of co-opetition and a lot of classical dynamics and ideas around competition don't apply. For example, the OpenAI Microsoft relationship is a very unique one. Co-opetition is probably a fair way to describe it. Microsoft's one of OpenAI's biggest investors, obviously, but also arguably one of its biggest competitors, right? And that's true for a lot of other companies doing things on the frontier in AI. And I think that part of the reason they do this is because I think that companies on the frontier realize that the primary competition to a new idea is actually just inertia and the status quo. Funnily enough, when you're fighting against inertia, people who would otherwise be your competitor are actually sharing the education burden with you and may actually be your primary collaborators. And so I like to think of things less that way. The way I think about things is one concept that's really important to me, in addition to that root node problems concept, is the concept of additionality in economics. And I think the idea is you want to be working on something that wouldn't happen if you weren't actually working on it. You want to try to make a counterfactual contribution. And the way I think about that is you start from what vision of the future is exciting to you. You then ask what needs to happen for that vision to manifest. You then say among the things that need to happen, among the balls that need to roll into place, like imagine like a billiards table being in a certain configuration, which balls are currently moving, which things are currently happening with the right velocity, meaning both speed and direction. And then you can say, okay, for the things that need to happen, these aren't happening fast enough, or I'm not certain enough that they'll happen, or this particular piece of the puzzle is not even moving in the right direction. It's moving fast in the wrong direction. And so you say, where can I apply force given my unique affinities and predilections? And I think when people do this, like a lot of the noise around competition, I think kind of falls away because you say, okay, is the world the way it should be in the category they care about? Probably not. And probably also, things aren't just headed that way fast enough with certainty. Probably there's room for you to push and apply force and try to help things move in that direction. And if it's a big enough vision that you're pursuing or a big enough contribution that you're trying to manifest, there's probably a lot of room for, there's probably more to do than there are people working on it, most likely. And so that's the way I think of it is I say, okay, what things do I think are not getting enough attention? Or do I not feel enough conviction will converge and that they're so important that I need high conviction will converge? And let me work on those things. And so funnily enough, most people would say that Foundry's competition is primarily the hyperscalers. In a classical view of competition that's just slightly broader, I'd actually argue that our primary competition for any cloud or any infrastructure service player is a model as a service company, right? Like OpenAI API is the primary substitute to using a GPU, arguably, right? Most people wouldn't think of things that way, but I think that's a more useful framing. And under that framing, but I don't think that's quite accurate because OpenAI has done more to grow interest and adoption of AI than almost anyone. And they've grown the pie a tremendous amount and pushed the research frontier and made us all inspired about what we can do to a greater extent. So I think the way we think about it is, okay, where are there gaps? Where are customers struggling? Where are things more difficult than they should be? Or where are there levers that should be pulled, things that should be done, questions that should be asked or envisage the cloud given the things that are different about AI workloads, for example, that we talked about earlier, that haven't been done? And by doing this, can we make a contribution? Can we move the needle on economics? Can we move the needle on ease of use in the ways I described? And can we make these things more possible than the others would be? And that's how I think about things. And it doesn't even feel like it doesn't feel like competition is a challenge when you're thinking of things that way. My belief is that if you create enough value, which you do by following those four questions I described, then it's actually relatively easy when you're creating a ton of value, if you're creating a ton of value, which is very hard, to capture some value. That's actually relatively easy. It's very hard if you're not creating value to capture value, perhaps. And so I think people get confused when they start the other way. So, for us, as we're solving people's problems and helping them do things they wouldn't be able to do in a differentiated way technically, that allows us to, we charge. And so some of that surplus we can reap as a company, and that helps us be viable and invest in more tech and grow our business and grow our team. I think it's relatively straightforward in that way. And so, we're very happy to work with our competitors, and to try to grow this ecosystem and try to address the challenges and pain points of users. And in many cases, we're not even tackling the same sets of problems. So that's how we think about it. That's not, so I can say more about that, but I can talk more about different parts of PaaS and IaaS and models of service if useful. But that's kind of the overall way that we think about this topic.
Yeah, no, that makes complete sense. And I guess sort of going into like the sets of problems you guys are working on to sort of apply force in this market, would it be like a fair assumption to say that like a lot of your guys' force and hard problems centers around this issue of like, can we build infrastructure around GPUs to utilize them better? Is that sort of the heart of the problem that you're solving?
That's a huge, huge part of it. Yeah, 100.
Yeah, and so let's maybe dive into that a little bit more about like this problem with like the infrastructure right now and like why these GPUs can't be utilized or like why they're not being utilized properly. And maybe even like diving into like maybe a concrete example, which is like I know you touched on some of this earlier, but like you have a cluster of GPUs, they're all physically connected. What's so hard about getting these to be utilized?
Yeah, for sure. Yeah, so one of the simplest points I think you're alluding to is even in the most favorable circumstance for high utilization, which is you have a pre-dictated, predetermined pre-training job, and you're going to rerun that over a long period of time, it's actually decently hard to achieve high utilization because of complexity and high failure rates specifically, right? So we've talked about this a little bit, Usman, you and I. And these GPUs, people think of them as chips in the mental model that we all have as chips, but they are systems. They're 70, 80 pounds, 35,000 individual components for each 100s. There's a lot of moving pieces. These different components have different coefficients of thermal expansion, and when things get hot, things stretch, and it's like these are complex physical systems. And one of the, I think, things that people have been shocked by is when they're trying to do frontier work in machine learning, they realize, wow, actually, this is quite complex. These things can fail, and that presents a very novel distributed systems challenge. One of the hacks that people have been employing en masse to address this challenge is they've kind of been trying to circumvent it by allocating lots of healing buffer, by setting aside, in many cases, 20% or more of their nodes as healing buffer so that if there's a failure, they can swap something else in and keep the training going. That's obviously extremely expensive to do. And sometimes, actually, there are horror stories where 20% may not be sufficient depending on the quality of the cluster that you have and how frequent failures are. And it's also the size of your workload and how synchronous it is. In some cases, I know of people who've gotten clusters of 3,000 GPUs and only been able to use 1,500 at a time. That's an economic travesty, especially if you waited 6 months for that cluster to be delivered and it's a 3-year contract or something. That's an economic travesty. And some SLA might not be sufficient from the cloud provider because your vision and your ability to manifest your vision is now imperiled. That's not great, right? So I think one of the things that I think we've done at Foundry that's a little bit interesting is we, as a very simple example, wanted to handle that on customers' behalves. For example, by allocating healing buffer, by setting aside those nodes for customers. But then we actually, as a cloud, can make the economics a bit more favorable by allowing that healing buffer to be used. For example, preemptively for spot workloads that are amenable to preemption. And then if there is a failure within a reserved node at the physical level, then we can swap that in virtually, swap in a healing buffer node, keep the training going, and the other workload is preempted and perhaps move to another node within the spot pool. That's actually a very useful thing, but these spot pools have to be maintained very delicately, have to be maintained thoughtfully so that you have sufficient capacity. You have to maintain also redundancy at different levels. And so it's an interesting scheduling problem, interesting allocation problem. But it's important. It's also important, though, that we make all this convenient for people. So, for example, for people using Spot, there won't be much Spot demand if preemption is happening too frequently and it's difficult to actually make forward progress. And so you have to create tools that make it convenient for the person using Spot, for example. So this is kind of one example of the types of things that are pretty interesting from a systems perspective, from a scheduling perspective, and how that enables a great UX, which is for someone using reserved nodes that they expect it to be up on a continued basis, they actually have that kind of relatively seamless and secure experience. It'd be very difficult to build a house if the ground was continually shaking and there was a constant earthquake, and that's what GPU failure feels like. It's like doing construction, like building a model on a faulty cluster is like trying to do construction in like a very, very aggressive, like very unstable fault zone or something like that. So it's very, very difficult for people. And so that's one example, and that's in the most favored case where you're trying to do a pre-training job, right? You're trying to run the GPUs at max utilization. You have a workload dedicated to it. It's so much more challenging when, for example, you're an enterprise and you had to buy your cluster defensively to provision for peak. But then there are natural ebbs and flows and the needs, of your team, of your research team or your organization to run experiments, etc., that lead to periods of underutilization. Pretty typical utilization, even for a dedicated cluster for a very sophisticated org, can be 25% or lower in many cases. And so it can be a difficult problem for a lot of organizations to handle. So there's a lot of underutilized capacity, and that's just for state of the art servers, data center GPUs. I'm not even referring to other compute of any form, but theoretically, cell phones, laptops, these types of things could be useful for workloads as well, and that's something we could double click on. It's an interesting lever. But even just talking about state of the art GPUs for dedicated pre-trained jobs, it's actually difficult to achieve the types of utilization that people would expect.
Yeah, yeah. And so you guys have built this infrastructure that one allows someone to come on the Foundry site and very quickly get access to a GPU. But in part to do that, you also have to help the people that have the GPUs, right? And so it sounds like you've built a lot of technology that helps sort of utilize these. Do you mind diving into some of those? Like, what are some of these things that you guys have built that your customers sort of don't see, but get to benefit the fruits from?
Yeah, for sure. Yeah, so just to expand on that, for a customer coming to Foundry, as I mentioned, we wanted to solve a few of these challenges, and so we've done a lot to reduce GPU failure rates. But then also we want people to have elasticity and great economics, so people can spin up short-term, long-term reserved allocations of clusters for really great prices, particularly for our healing buffer. That can be 12 to 20x lower than the reserved long-term reserve price. That's substantial for companies doing meaningful things. And then for spot nodes, people can, if they have a workload that's amenable to preemption, that has low opportunity costs, and so they can use healing buffer nodes preemptively at a price dictated by auctions and markets. Though we've done a lot of interesting auction theoretic work that I'm sure we'll talk a lot more about over time. But to basically say, hey, the incremental price of this is just the incremental cost of power. And from there, we just let it be dictated by the price be dictated by auctions and market dynamics, and allow the GPUs to flow to the workload with the highest, where their basically surplus would be maximized in the system. It's a very neat and efficient system. It removes a lot of the friction for people trying to use GPUs. I think it's a bit cleaner and creates some transparency, and I think people really actually appreciate it. And we've, I think, attracted a lot of awesome users who like this mechanism. So that's one piece. Now, for all this to work out, there are a few pieces that are necessary. And so the analogy that I've invoked that seems helpful for people to talk about this is an analogy of parking lots. And so in very funny ways, the GPU cloud business is kind of like the parking lot business. There's kind of the two models, right? There's the primary model in the standard cloud is pay as you go, on demand, as it's called in the typical cloud. The rates are usurious, and you may or may not get a server when you need it or a spot when you need it. On the other hand, if you want to avoid that fate, you can get a reserved allocation, a reserved parking spot. You're paying for it on a monthly basis. Your price per unit time, per hour, for example, might be lower. So instead of $12 an hour, maybe you're paying $4 an hour. But because you're paying for it even when you're not utilizing it, your effective price might be higher. So for example, if you're using it 25% of the time, 40 hours a week, like a typical office worker, your effective cost might be $16 an hour, which is actually higher than $12 an hour. But maybe that's still justifiable, even if you're aware of that challenge, given that at least that way you have a spot when you need it. You don't have to drive from lot to lot, drive past lot full signs of looking for an open spot. And so that's kind of the state of affairs that people are dealing with right now when trying to think about GPU procurement. One thing that we did is introduce a third type of utilization category, which is you can kind of pay as you go park in someone's reserve spot. I'm sure you've driven through reserve parking spots going down, down, down deeper into the basement and driven by all these open reserve spots, being frustrated. It's a bit of a waste. Part of the reason for that waste is it'd be very difficult, very inconvenient for everyone involved. If you came to your reserve parking spot and someone was parked there, that'd be inconvenient. It'd also be inconvenient if you had to, for example, if you were parked in someone's reserve spot and someone called you, some parking attendant called you and told you to move your car on short notice, like that'd be inconvenient. So long story short, you need some type of automated mechanism if you wanted to allow people to park in someone else's reserve spot to get higher effect to unlock more effective space and reduce prices for everyone. You need to do something to manage the spots well, and you need to treat a parking spot. You need to be fungible. You need to treat it more as a priority rather than as an actual allocation. You need to manage the open spots. And so maybe you can imagine that a Japanese style elevator parking where you have have you seen that before? Like elevator parking? Yeah, maybe that'd be a more efficient system than having some notion of just pure reserved, as long as there's some cars, as long as you maintain enough buffer, or there's some cars where someone maybe is willing to come get it on short notice, for example. But you basically, if someone needs to move, you just move it to a different spot when someone comes for their reserve spot. Like if you did that, then maybe you could actually have a lot more effective utilization. People paying as you go in someone's reserved spot could pay $7 as opposed to the typical 12, saving $5. The person paying 4 typically can make 5, for example, and then the lot can make a couple bucks to support building new infrastructure of this form, etc. And so that's kind of a win-win for everyone, and that'd be pretty awesome. And that's kind of part of what we've done with a lot of the work that we do around spot usability and scheduling, is kind of make this system work for everyone and create more effective space. And that also allows us to monetize these GPUs better, which we use for ourselves, but then also that allows us to give that to other people and kind of create the supply side of our cloud as well. That's an interesting piece of how we're scaling our business in a really capital efficient way. That's that we can talk more about.
Yeah, yeah. Well, it sounds like we need Foundry for SF parking garages too, because that does irk me a lot when I'm driving by looking for a spot and there's a bunch of reserved parking spaces. But let's actually talk a little bit more about sort of the supply side of it a bit more, or more than that, like at least the logic that I've been following so far, which is like, okay, GPUs are more than chips. They're these very complicated systems that you sort of have to deal with. And they fail a lot because they're very complicated. And as a result, you have this concept of this healing buffer, which, you're sort of buying extra just so that you can be safe in the case of an emergency, right? And you guys have spent a lot of tech in trying to like first sort out like how can we tap this healing buffer for someone else while you're not using it. I've also backed it with a very amazing auction model to make sure that the incentives all align here, thinking about it more as like a priority or queue system rather than just like a spot. But I am curious that that does kind of invite some degree of risk, right? So like if I'm someone on the if I'm someone that has a bunch of GPUs and I recognize that, hey, like a lot of my GPUs are not being utilized, maybe I should hand it over to Jared at Foundry to like make me a couple, to get some value out of this. Aren't you nervous though that like what if I do need it and this is being used by someone else? Like that puts a lot of pressure on you guys. Like how do you go about like convincing these people to be down for that?
Yeah, for sure. Yes, let me explain that. So that's actually a really astute question. I like that. So classically, maybe I'll introduce this idea that within training and inference, which is a distinction that we draw a lot in the ecosystem, there's actually different types. There are different types of training workloads and different types of inference workloads. And one way which you can distinguish these different classes of workloads is in terms of their tolerance to preemption and resumption, and for example, their need for low queuing times. That's one way of thinking about it. That's not quite right. Maybe another would be, do you care more about latency for allocation or more about kind of throughput for this workload? That's a big difference. And there are actually some types of training that look more like inference and vice versa. So for example, there are types of training workloads where you need very fast allocation and you actually don't need as much efficiency, for example. One example would be verification training and debugging, which is like before you launch the big training run, maybe you need to first run an interactive job to confirm that there are no bugs in your code before you YOLO send it on the big cluster. If that loop that you're running to do development is too slow and queuing times are long, you're not very happy per se. However, when I'm launching the big job, that big job might run for 6 months, and it doesn't really matter to me if it takes you 30 minutes to an extra hour to run some scheduling algorithm before you actually place that job. Obviously, right? That's especially if that 30 minutes of thinking up front would actually allow you to run that 6-month job in like 5 months. And that's an absolute no-brainer, right? And so this is an important point. There are different types of workloads, right? And so as an example, maybe also I have in my typical flow as a researcher a lot of workloads that are preemptible. I just need them to finish by some deadline. So I launch the workload at the end of the day. It's 6 hours worth of total work on some number of GPUs. And as long as it's done by the time I come back the next morning, I'm happy. And so depending on how much that person sleeps, if they go home at 8 p.m. and come back at 10 a.m. the next morning, that's 14 hours. This is how a workload can run at any point within that range, or you can start it and stop it, etc. They'd be happy either way. Whereas there are other workloads that need to run instantly, for example, for live serving of requests. And so having the flexibility to move things around is actually quite powerful. And if you told me that, hey, Jared, you're launching a workload at night, and when you come back tomorrow, it'll be done, but I might pause it in the middle, but if I do so, I'll reduce your costs by 10x. That's a no-brainer, potentially, right? And so, long story short, that's one of the fact that there are different workloads with different SLAs, with different affinities, with different contiguity requirements, etc., actually creates room for scheduling algorithms to place these in a way that maximizes surplus. So that actually is why this is such an interesting problem, why there's such a room to make a contribution that we pursued. Is they're not all workloads are the same in terms of what they care about, in terms of their shape and their size, in terms of the value that I attribute to them. And so that's something that you can take into account when scheduling. Yeah, so that's kind of a way that we think about this.
Yeah. No, that makes complete sense. And I guess final two questions here. I mean, you kind of talk about it here with like scheduling. Obviously, you guys had to come up with this whole bidding and auction system as well. What's sort of next for Foundry? And I guess this kind of touches into those listening in who are now completely sold on Foundry, I'd assume, and are like, okay, I need to work here. What are the hard problems left if you guys have solved these already?
Oh, there's a lot of hard problems left. We've not solved everything by any means. So I'm excited if people find this interesting. Yeah, I think what we're doing is quite difficult in a lot of ways, but it's quite inspiring. And we are lucky that even at this current inchoate state of development, we've been able to make a difference for so many customers, and I think we can scale that even more. But yeah, there's a lot of problems. Like there are a lot of aspects. There's a lot of work to do on kind of feature parity compared to the major clouds. There's a lot of advanced features for things like identity access management. These aren't the most attractive things per se, but there's a lot of just work to do to make cloud infrastructure really usable for the most critical workloads at scale in production, things that really matter, for example, to large enterprises that we're working on. And so there's that feature parity work, which we have to balance with a lot of very interesting kind of future forward work around new techniques that otherwise wouldn't get done. So there's a lot of baselining work, and that's actually one of the challenges. I think someone instead at Foundry should be excited to do. There's some amount of work that isn't the most appealing on the surface, but is very impactful. This alone should be kind of impact driven, very much, and that's how we think about things, and have a almost servant mentality towards our users. But there is a lot of very interesting work. There's a lot of open questions on the auction and mechanism design side that we're starting to tackle, but a ton of open questions there, and I think that's something that appeals to some of our current teammates, and I think attracts them as well. Like the problems that we work on sit at a very novel intersection between machine learning, and architectural questions and machine learning that are very deep, systems, and placement and scheduling questions, but also mechanism design and auction theoretic questions that are pretty novel. And so it's at a very interesting systems and theoretical intersection. I think is very novel, and there's a ton of open questions in this setting. And we're making continued progress and discovering new ideas and employing those and seeing the gains that confers. But there's a lot of room to push on those things more. So that's extremely exciting. There's a lot of kind of hardcore systems work to do on better mechanisms for improved virtualization, greater security, lower VM start times, more portability that creates more degrees of freedom and makes a lot of hard scheduling problems a bit easier. There's a lot of room to push the system, and we're extremely early in our agenda. But I think we've made a lot of early progress, and we're provide something very useful to people. But yeah, I think people should be excited that there's a lot of hard problems, but it's definitely difficult. And I think we like to have a small team of really smart people who are willing to hold a lot of scope in their minds and grok everything from a lot of UX considerations down to systems and economic considerations. They have to kind of hold that whole state of the system in their minds and reason about it and make trade-offs that are complex. And so we like to have a small, highly competent team that's relatively flat and high agency.
Yeah, absolutely. And just I guess the final question I have for you here is I'm again from the perspective of someone who's considering to join on, there's obviously a lot of what they've heard today is, how Foundry is really sort of looking at like what is the real bottleneck with these GPUs is that they're underutilized, and you guys have built all the infrastructure, and I'm talking like the technological infrastructure to utilize these GPUs, which is no easy work, and then have built all of the economic infrastructure around that as well. What would you say to people that maybe consider that like, okay, this is one approach to solve this problem, but what if GPUs themselves sort of don't have this like failure rate anymore? Like, what do you think about that? Like, are GPUs always going to have such a high failure rate? I know there's a lot of buzz about AI specific chips and how they're much more utilized. And I'm curious, like, where you sit in all of that.
Yeah, for sure. Yeah, I think failure is just one small piece of the utilization equation. Maybe one way to put that. So I'll make a couple of points. I think there's a few ideas undergirding what you're saying. Maybe a slight reframing is more fundamental than if there wasn't failure. Is like, what if there were more GPUs and there was like an extreme surplus, or GPUs were cheaper, or AI compute was cheaper? And this actually gets to a more thematic point, which is I think that one of the ideas I kind of alluded to earlier is this idea of Jevons Paradox, and I'll just invoke it here, which is that It's one of the ideas in economics that I discovered by happenstance in my ML research work. I was kind of subject to it in a funny way, but is finding a lot of my thinking about technology. And the basic idea is that Jevons Paradox tries to address the question of why come certain prices or why come certain markets behave differently than you'd think. So why come, for example, when you make highways twice as big, traffic gets worse? Or when you cut the price of oil consumption goes up by so much? Why does that type of thing happen? And I think part of the answer is actually very self-explanatory when you think about it, which is that when you make something 10 times cheaper, you're actually improving the ROI. When you improve the ROI, it probably makes sense, as long as there's not an S-curve to that improvement, to actually invest absolutely more, not just to actually ramp up your investment. So if I was investing $1 million before and you improve the ROI, actually I should dedicate more of my assets to that thing. And so when you improve the ROI of something, when you make something more efficient, then there actually might be a super linear increase, kind of counterbalancing increase in demand for that thing. And I think that's one thing in this field of technology industry. Apparently, early in technology, people were wondering whether technology would ever be a big industry because of Moore's law. We were depreciating ourselves out of existence, making the chips, right, kind of twice as effective every 18 to 24 months, cutting the cost. And that people were thinking, okay, technology industry is going to depreciate itself out of existence, and that's obviously not what happened. Technology is more important than ever. And same with there have been similar discussions around bandwidth and some of these things over time, which had interesting economic evolutions to the story. So there was some bumpiness, etc., in the stories. The point being, I think when you make AI compute 10 times cheaper, I think that actually the demand for doing work with AI will actually grow by more than 10x. And so I don't think it's a zero sum way. I think actually things that we're doing to find no better ways of doing things actually create more opportunity for us and for others in the ecosystem. And so, part of the way we think about it is like it'd actually be very, very good if utilization, if the GPU failures went down, if there were more GPUs in the world, etc. And I think that what we'd find is that people would have many more ideas for what to do with GPUs and compute, actually commensurately, actually like super linearly more. And these steps of scheduling concerns will be more and more important. That's what I hope, is that things like like ChatGPT will be much more common. Things like AlphaFold will happen 10 times as often. And scheduling will be actually more and more important. And so that's I didn't do your question full justice, but hopefully that addresses.
No, that absolutely does. Yeah. Yeah, no, that makes complete sense. I guess, we've already taken a lot of your time here and we appreciate you coming in. For those interested in joining, what would you say is the best way for them to reach out to you or the team? Yeah.
Please, reach out. I think we'd be excited to talk to smart people who find these types of challenges enticing. Reach out to Michael at mlfoundry.com, and that's the best way to get in touch with us. And we'd be super excited to connect and talk more about things that we're working on, and really excited to connect with people who are looking to push this mission with us.
Awesome. Awesome. Sounds good. Well, thank you so much again. And we are looking forward to all that Foundry does in making AI accessible for everyone.
Thank you, Usman. Appreciate it.